Hi, I'm Varun Joshi and welcome to day 12 of our Certified Kubernetes Administrator 2025 course. Today we'll dive into Kubernetes services and explore why they are crucial for communication within and outside the cluster. We'll break down different types of services like ClusterIP, NodePort, LoadBalancer, and ExternalName and understand when to use each one. What you see on screen are two worker nodes, and these two worker nodes are running two deployments. One deployment is named front-end deploy, which is using the Nginx image, and the second deployment is backend deploy, and it is using HashiCorp's HTTP echo image. First deployment has 4 pods and the second one has 3 pods. If you look in this diagram, there are a couple of challenges with this diagram. If pod 1 wants to communicate with any of the pods in backend deployment, then I would have to supply or hard code the IP of these pods into these pods so that they can communicate with this. For example, if I'm using pod 1, then pod 1 would have hard coded IP address of pod 3. Now this is not something that will be a workable solution in the long run, because as you know, pods are ephemeral. They do not have stable IPs and host names because they come and go. If pod 3 dies and another pod comes up, then it will have a different IP address and host name. Hence, the first challenge with this scenario is pod IPs keep changing. And the second scenario is, if I am running my front end here, then I would want some way to expose my front end to the external world so that people can access my front end from outside. And the second thing is, if I have a backend deployment, I would want a way via which the front end can access the backend seamlessly. In this current scenario, there is not a way via which I can load balance the traffic that is coming from front end across backend, or load balance the traffic that is coming from outside to the front end. Before we talk about how we solve these challenges, I wanted to take a moment and go back in day 1 and day 2 where we learned how these images are created and how these are pulled, just to refresh your memory. Now, developer would write the code, then the developer will create a Docker file. This Docker file has both code plus the dependencies. Then we create a container image using that Docker file using the docker build command, and once the image is created, you can create a container from that image and also push the image to your image registry. Once the image is pushed, it can be used anywhere. Any machine which has Docker engine running can use that image. Now that we have shifted our base to Kubernetes, I want you to know that in Kubernetes, the default image registry is Docker Hub, which is why when you write nginx:latest, it pulls that image from Docker Hub without providing the pull path for Docker Hub. In this example, docker.io is for Docker Hub. Library is the namespace within Docker Hub which holds the official images, which is why the Nginx image is held in this namespace. If I talk about the second image that we will be using in our backend is called HTTP echo. Why we are writing HashiCorp here is because this image is held in the HashiCorp namespace. If you see this, docker.io is for Docker Hub. HashiCorp is the namespace. Namespace is named based on the user or on the organization. Since this image is owned by HashiCorp, we have HashiCorp here, and then is the image name. Since for the Nginx image, the namespace was default, we just wrote Nginx. For HashiCorp, this image is for HTTP echo. This image is held in HashiCorp namespace, which is why we are using HashiCorp here, since HashiCorp is not the default namespace in Docker Hub. Now, another thing I want you to understand is we have been using Docker to create our container images, but there are other alternatives as well. You could use Podman, Builda, Canico, and there are many more. However, Docker is the most popular choice, which is why we used Docker. If we were using any private image, private images are images that are held in private registries. These images, Nginx or HashiCorp, are held in public registry. The images that we are using here are public images. If I go to my Chrome browser and go to this HTTP echo image, you see HTTP echo is an in-memory web server that echoes back the arguments given to it. You see, if you want to pull this image, you use HashiCorp /HTTP echo. Let's go back now. Yeah. Now, if you were using your images that are private, then you would have supplied the namespace name and then your image name. If you are using a custom Docker registry, if you are using, for example, let's say ECR or ACR, then the cloud provider would tell you how to pull container images. Then you would write that image path here, and then you will also have other objects which will hold the authentication, Kubernetes object. We'll see those objects later in this course, but for now I want you to understand that when you have Nginx image or HTTP echo image, these images adhere to the same process when the owner would have built these images. Okay, let's see how can we solve these challenges. Now you see that before each deployment we have placed a service. You have a front-end service that is placed before the front-end deployment, and there is a back-end service that is placed before the back-end deployment. What do these services do? First is stable IP address and DNS name. Whenever front-end wants to talk to the back-end, front-end will just supply the DNS name of the back-end service, and then back-end service in turn will forward the traffic to a healthy pod in the backend deployment. This is how you have decoupled your front end and backend service here acts as a glue which helps front end to communicate with backend. Similarly, you have a front end service placed before front end deployment. If external users are accessing your application, then they will hit the front-end service, and then the front-end service will distribute the traffic across these 4 pods. So Kubernetes service will provide you stable IP addresses and DNS names. Second, it will also do load balancing, and Kubernetes service can be used for both internal and external communication. Here you can see internal communication is whenever front-end is talking to the backend. External communication is when a user from outside is talking to the front end. Now let's see how the flow would look like. A user will access the front end service. The front end service will send the traffic to the pod that can answer that request. Let's say it sends the traffic to pod 1. Then pod 1, let's say, wants to request backend to apply a specific business logic. Then the request will, let's say, go to backend service. Backend service will forward that request to any of the healthy pods, let's say pod 3. And once pod 3 sees the request, pod 3 will process that request and send that back to the pod that initiated that request. Let's say pod 1 was that pod. And then pod 1 will send the request back to the user. So this is a high level flow. Now there are different types of Kubernetes services that can help you achieve this sort of architecture. Okay, now let's scroll down. The first service that I want to discuss is the ClusterIP service. Let's first read the definition of this service. Exposes the service internally within the cluster, allowing pods to communicate with each other but not accessible from outside. Let's go to the right side and see an analogy. Here what you see is there is an office building complex. This office building complex has 2 buildings, building 1 and building 2. Each building has certain departments, and 10, 11, 12, 13 are the extension phone numbers via which these departments can reach each other. When HR department wants to speak with finance department, they can just dial 11 and reach them. Now here, what are these extensions doing? Extensions are providing a means of communication within the office building complex. Similarly, when we talk about Kubernetes, this office building complex is like a Kubernetes cluster. These two buildings are like nodes that you see here, and these departments are like pods in Kubernetes, and like we know, pods are deployed as part of deployment. If pod in front end wants to speak with pod in backend, then they will send the request to the backend service, and then backend service will send the request to the backend pod. Similarly, in this architecture, when HR department wants to communicate with finance department, they will first send the request to the extension phone, and then the extension can be picked up by anyone in the finance department and the call can be answered. I hope this analogy is making sense to you. Now that we understand the high level flow of the ClusterIP service, let's move to the low level flow and understand how this works end to end. Here in this diagram, I have shown two deployments. There is a front-end deployment and there is a back-end deployment. Both these deployments have 3 pods. First deployment has the Nginx pod, and your backend deployment has HTTP echo pods. Another thing I want to highlight here is right now our Nginx is also a web server and backend is also a web server. However, this HTTP echo web server can be used to echo anything that you want. In our example, these will be echoing this is a backend. That's it. Otherwise, in real production world scenarios, you would have an actual backend that is applying business logic. To maintain simplicity and to concentrate on Kubernetes, which is our task at hand, I wanted a very simple example so that we spend more time understanding the concepts rather than understanding the code and the images. Okay, let's get back to the crux here. If you see on the right, we have the similar terms. We have API version, we have kind, we have metadata, and then we have spec. We'll write this YAML from the scratch, but I'm telling this because this diagram will make much more sense when you understand this. So I have under the spec section, I have type, ports, and selector. My type is ClusterIP, and ClusterIP service is the default type. If I would not have written type, this would have created a ClusterIP service itself, but for completeness I always prefer to write the type. Then you have ports. Under ports I have protocol listed as TCP. Then port is 9090. The port that you see here is the port of the ClusterIP service itself. You see the comment here, exposed service port. Then you have target port here, container which will answer the request, or the containers that will answer the request have 5678 as the port number. Selector is app is equal to backend, where we are saying any pod that has app is equal to backend label, that pod will fall under this service. Just a small correction in this diagram. This should have been 1096.74.12. Let me just quickly make that correction. I was bootstrapping different clusters and different deployments and services. So these IPs kept on changing. So pardon me for that. Now let's say this Nginx pod 2 wants to initiate communication with backend. What will happen is we have a backend service just before the backend deployment. The Nginx pod will be configured whenever you want to speak with backend. You remember we said that the code plus the dependencies are part of the image. Here, whenever front end wants to speak with the backend, the dependency is it should know how to reach the backend. So the application code will have this configuration that whenever you want to reach backend, you reach out to this service and this service will know what to do. If you see here, the request goes to backend-svc:9090. Why 9090? Because I have said that this service will listen on port 9090. Now your pod does not know the IP address that is for this DNS name. It will send the request first to the core DNS. Core DNS will resolve the name to an IP address. In case the name is cached in this second pod, then the request won't be sent to the core DNS, like how DNS functions. Once this pod knows the IP address, then the request will be sent to, let's say, 1096.74.12. Why this IP? Because if I run a describe on my service that I just created, I come to know that the cluster IP assigned, which is dynamically assigned by Kubernetes to this cluster IP, is 1096.74.12, and this request will be sent to this service. Then this service will then send this request to any of these pods. In our example, let's say the request is sent to the pod 3. Before sending the request here, it will change the destination IP to the IP of this pod. Let's say this is the IP of this pod, and it will also forward it to the correct port, because we have specified that the target port is 5678. Now let's go here and let's see what are the components inside this service. We have supplied selector as app is equal to backend. The name is backend-svc. Then we have the type is cluster IP. Then we have the actual IP of the service itself, that is 1096.74.12. Port is set to 9090. This is the port on which this service will listen, like we have specified here, 9090, just the port. When we talk about target port is 5678. And endpoints, now the deployment which has the pods that have app is equal to backend label had 3 replicas, which is why it is showing 3 pod IPs here. If I had 10 replicas, for example, we would have seen 10 endpoints here. Let's now go to our Visual Studio Code and create a backend deployment and a backend service. I'll go here, I'll close this readme.md file for now. I have already in day 12 I have created these skeletons. So let me go to the backend skeleton. I'll quickly remove whatever I have written. What I'm doing is I'll write the deployment YAML from the scratch, although we have practiced it in our deployment lecture, but I'll write the backend YAML for the deployment from the scratch, and also we'll write the service YAML from the scratch. So let's start with API version, and we know that to check the API version and kind, we can just quickly run. So let me go here. We can run kubectl API resources. Here we can see that when we talk about deployments, they fall under the API version apps v1, and D is uppercase is the kind. Let's go here. API version is app/v1, kind is deployment, metadata is 2 spaces, name is, let's say, backend deploy. Then we have a spec section. Under spec, we know that I'll have first 2 spaces, replicas, and let's say that I want 3 replicas. Then I'll have selector will have match labels. Match labels would be, again I'll hit 2 spaces, app is equal to backend. Then I'll have template here, and in template I'll define what sort of configurations the pods that are part of this deployment will have. I'll again have metadata, and under metadata I'll add certain labels, and these labels should match the selector. So we'll have app is equal to backend as our labels. What we are saying is this deployment will manage any pods that have app is equal to backend label. That is why we are adding app is equal to backend label here. Then we'll go and add the spec section here. Spec section will have our containers, so I'll write containers here. Then again 2 spaces, name I'll write backend container, and I'll have to add a space here, and then I'll add the image name, and let's say the image is, we're talking about the backend, so we'll have HashiCorp's http echo image, and we'll also supply certain argument, and let's see what that argument is. I will say the text that you should be displaying is hello from backend. Now, if you see this the page for this image, you will see that you can supply the text as argument, and whatever text you want to supply you can. Since we are simulating the backend, we are just printing hello from backend. This looks good. Now let's create the service YAML. What I'm doing is I'll create the service YAML as part of this backend.yaml file. This backend.yaml will hold the configuration files, the manifest files for both my backend deployment and backend service. So I'll add 3 hyphens which acts as a YAML separator, and then I'll start writing the manifest. I'll first create the skeleton, API version, kind, metadata, only if I could spell right, metadata, and have the spec section. Let's fill these things now. For API version, let's again go back to our command line. We see that here we have services. The short name for them is SVC. They belong to the API version v1 and their kind is service. So let's do these things. Let's fill these things. So version is v1, kind is service with uppercase S, metadata, we'll provide the name of this service. I'll hit enter and give 2 spaces, then I'll write name. I want this to be called backend-svc. We are writing svc because svc is the short name for services, and here we have written -deploy because deploy is the short name for deployments. We go to spec section now. In spec, we'll have 3 main categories. First is type, second is ports, third is selector. Now, I am pretty high on acronyms. So when I was learning services, there was something, I used to work in VMware, and there was something called transparent page sharing. Transparent page sharing was associated with the memory. Anyway, long story short, so TPS was what transparent page sharing was called. Hence, I remembered whatever is there in the service spec starts with T, P, and S. That's how I remember type, ports, and selector. Now it is a habit that I keep on writing. But when you pick up these manifest files after like 2-3 months, you tend to forget what were the instructions that were used. So hence, this is a small acronym that I used to remember what do you have inside services. And I think I similarly told you how I remember these 4 blocks: API version, kind, metadata, and spec. We have something called AWS KMS. That's a service. So A is API version, K is kind, M is metadata, and S is spec. So, I mean, if these acronyms help you, be my guest. But if you think that this is the weird way of learning, then please ignore this. So I'll go to type. In type, I'll write ClusterIP. I want you to concentrate on the uppercase C and the uppercase IP here. Then inside ports, I'll have certain sections. The first one is protocol. Again, this is optional. I think TCP is the default one. So I'll write protocol is TCP. Then again, the port, this is the port that this ClusterIP will be using. Let's say this is 9090. Then you have a target port. It's 5678. Then selector, we know that this service should be catering to the backend pods. Hence, backend pods have a label app is equal to backend. So we would want this service to select all pods that have the label app is equal to backend. So labels and selectors work the similar way. Anything that has selector defined as app is equal to backend will select these pods. First, the deployment is selecting these pods because deployment is supposed to match anything that has app is equal to backend label, and the pods that will be created by this deployment will have that labels. Similarly, I want these pods to also be selected by this service. Why I want that? Because I want any traffic that is coming to this service should be distributed between the backend pods. Hence, I'll write here selector will be is equal to backend. It is that simple. Now you understand how to write deployment YAMLs and service YAMLs. We also learned that you can have both these YAMLs in this single file. That is what we are doing. Now what we'll do is we'll go to our console and apply this backend.yaml. If I go to my console and clear my screen, I am already in day 12. Day 12 is where these files are located. So let me quickly run cube. Let me just zoom in a little. Yeah, I'll just clear my screen now. I'll run kubectl apply -f. I'll type backend.yaml and I'll hit enter. As soon as I hit enter, it says that the deployment is created and also the service is created. Let's do one thing. I'll now run kubectl get svc backend. You see, this tells me that the service backend service is of ClusterIP type. The ClusterIP for this service is this, and this service listens on port 9090. That is how we have defined this service to be in this YAML. If I want to check some deeper details, let's see if -ovide works here. -ovide just provides us one additional column, that is selector, and this is selecting any pods that have app is equal to backend label. Now let's also run a describe on this service, kubectl describe. Now that we know that the short name for service is svc, we can just write svc and backend svc is the name of the service. I hit enter and I see that name is the backend service, selector is app is equal to backend, it's a ClusterIP type, then the IP of this service is this, and this service is listening on port 9090. The key thing to understand is port here defines the ClusterIP port, not the container port. Container port is the target port, which is 5678 in our example, and the endpoints that are part of this service are these. These are the IP addresses of the deployment that the backend deployment created. To be sure, let me run kubectl get pods -ovide. -ovide will also give me the IP addresses of those pods. If you see here 10, 244, 2.3, 2.2 and 1.2. So you see here 1.2, 2.3 and 2.2. All these pods will be listening to traffic for the backend service. I hope everything is glued together now. Let's do one thing. Let's create a test pod and check if everything works as expected. What I'll do is I'll reuse kubectl run -it my nginx, the name of this pod, and the image that will be used will be nginx --. The command that I'll run is bin sh. I'll hit enter. I'm inside this nginx pod. Okay, now I'll run curl backend svc. I'll hit enter. This did not work. Now why this did not work is curl by default sends the request to port 80, but we have said that this backend service listens on port 9090. So let's hit Control C here. Now I'll write curl backend -svc on port 9090. If I now press enter, hello from backend. So this is what we had configured. Now let me quickly hit exit and show you what we have done. If I run kubectl get pods -ovide, let's write that. You see here I have 3 pods. These 3 pods are part of backend deployment. Then we create a my nginx pod just for testing, so that we can test that our backend service and backend deployment are doing what they are intended to do. We saw that they are doing what they're intended to do because when we wrote curl backend svc :9090, we got a hello from backend message. And why hello from backend? Because this is what we configured this container to do. Now I hope ClusterIP is understood. Now we'll move to the next service type, which is the NodePort service. Very simple to understand. Don't get intimidated with this diagram. We'll dissect this step by step. NodePort service. What is the definition of NodePort service? Exposes the service on a static port, and the range of those static ports are 30,000 to 192.168.1.32767. On each worker node's IP, each is the keyword here, making it accessible from outside the cluster by using the format NodeIP:NodePort. NodeIP:NodePort. So we can dissect from this definition that you can use NodePort service to access your deployments externally. So this part is understood by this definition. Let's now see the analogy to understand this. We have the same setup. We have an office building complex. We have building 1, building 2. We have different departments, and now we have added 2 more things. One is the front desk and second is a receptionist in each of the building. When an outside user, previously all were talking to each other on extension phones, but now that we have added an external user, when external user wants to speak to the HR department, the user will have to call the front desk phone, and once user dials the front desk phone, there will be a receptionist that will hear, okay, you want to speak to HR department, let me dial 10 and transfer this call to the HR department. The key thing to understand is, even when you have a front desk phone here, you still need the extension of the HR department to transfer the call entirely. The user hits the front desk phone, the receptionist transfers the call to the HR department. This is how it works. If let's say user was dialing building 1's phone and building 1 was down, in that scenario, user should also have the front desk phone for building 2. If there were 10 buildings, the user should have had the phone numbers of all those 10 buildings, because we don't know, maybe some buildings would be down. In that scenario, user should have all the phone numbers of all the buildings. That is understood. And if we relate this to Kubernetes, buildings are acting as nodes, office complexes are acting as the Kubernetes cluster, and then these are your pods, and these 10, 11 are your extension phones. The front desk phone here acts as the NodePort, and that is our topic in hand. If I now go to my Kubernetes cluster, you see the diagram here. We have a front-end service that is fronting the front-end deployment. We have a back-end service that is fronting the back-end deployment. And then we have 2 nodes here. User is hitting, in this example, node 1. And then node 1 is transferring that to front-end service. And then front-end service is passing the traffic to the appropriate deployment. I said in this analogy, the extension phone number and the front desk phone number, both are used for this communication to happen. The call first goes to front desk, and front desk then transfers the call to the correct extension. In this example here, NodePort is built on top of ClusterIP. So first the communication will go to NodePort, and then internally NodePort will be using the ClusterIP service to transfer the request to the appropriate front-end pod. Because NodePort is used to access the cluster from the outside, but we discussed before that any intra-cluster communication between deployments, they go through ClusterIP service. Now let's dissect this concept in this diagram and understand this. Firstly, before doing anything else, I want to show you the YAML for NodePort. It looks similar, if not same. The changes that I have done is, in type, instead of ClusterIP, you have NodePort. We have added one more line here, that is NodePort, and the NodePort that we have chosen is 31,000. Let's see how this communication works. In this example, I have taken 3 nodes. I have shown nodes here, but you know that all these deployments are running in these nodes. So let's see what is happening in this diagram. We have the front-end deployment, we have the back-end deployment, and this part of this diagram up till here is taken from our previous discussion of ClusterIP. We now have this added here. These are your 3 nodes. For example, if I go to to my Kubernetes cluster here. If I run kubectl get nodes -o wide, I'll see that I have 3 nodes and these are the internal IPs of these nodes. Similarly, 2, 3, 4, you see here, I have added 4, 5, and this should be 6. Pardon me for that. I have 3 nodes here. These IPs could be any. These are just for example. And let me just, for simplicity, let's call this exactly like they are here, 2, 3, 4. Let's call it 3, 4, 5, because I'm calling it 3, 4, 5 because I've seen the request here is formatted as .4, so I want this node to answer that request. 0, 4, 3, 4, and this will be 5. Okay. Once the NodePort service is created, like I mentioned, user can access your deployment using any of the node IPs, not just second node's IP. User, if node 2 is down, could use node 1 to access the resources or node 3 to access the resources, like we discussed in the analogy. If building 1 is down, then the user must use building 2's IP. If building 2 and 1 both are up, then user can use building 1 as well to reach the HR department. Similarly, in our example, if node 2 is down, for example, then user must know the IP address of node 1 or node 3 to access the frontend. The request first goes to 172.18.0.4:31,000. Once this request reaches the node, what will the NodePort do? NodePort will forward this request to the cluster IP. Now, Varun, but we did not create a cluster IP for front end. But whenever you create a NodePort service, a cluster IP is automatically created. The request then goes to the cluster IP, and from that cluster IP, the request goes to the appropriate pod. Now let's see this here. I have done a describe to the front-end service. This is the front-end service that we created. I have done a describe. You see here, this type is NodePort. The selector is app is equal to front-end. And you see here, there is a cluster IP created. We didn't ask to create it. This is created automatically because NodePort is built on top of cluster IP service. The port here is 80. 80 is something that we have defined as the cluster port here. You see, we have defined a port here, 80, and this is the cluster IP port. We discussed this in the previous section of cluster IP as well. Then we have the target port. Here, the target port is 80. You see, cluster port and the target port will often be same. This is because to maintain consistency, because cluster port could have been 8080 as well, but to maintain the consistency, usually what you would see is port and target port are same. In our previous example, I deliberately have kept these things different so that you can understand the concept first, but when you see the real world examples, there could be scenarios where you will see that both these ports are same. So I don't want to be confused at that point of time. Then we see that the node port is 31,000 and the endpoints are these 3 pods, and the endpoint, you see the target port is also mentioned here. Now let's see how the traffic would flow. The traffic will first go to 172.18.0.4:31,000, and then port 31,000 will say, okay, I can forward this request to the cluster IP. It will forward this request to 1096.199.133:80, because :80, why? Because 80 is the cluster IP port. It will forward the request to port 80, and then that cluster IP will say, okay, this request can go to any of the pods, and let's say it chose pod 3, and then again the destination IP will be changed to 10.244.1.10, which belongs to pod 3 in our example on port 80. This is how this pod answers the request. As simple as that. If you see here, the request first goes to NodePort, then it goes to cluster IP port 80, then it goes to port 80 of the actual pod. As simple as this. The request will be, then once the front end has received the request, it will communicate with the backend if it is needed. let's say user wants, let's take the e-commerce website example here again. Let's say user wants to see this is wish list. Then the traffic will go to the backend deployment using the backend service. It will follow the same process. I hope now things are getting connected. Let's write the YAML for this and see how it works. Now I'll go to Visual Studio Code. I'll open the front end and you see the deployment is already written and the service definition is also written. We will not write them from scratch, but what I'll do is I'll just split this to right. I'll close this so that you can compare these YAMLs. If you see here, everything remains the same. We just have type NodePort. This is changed, and we have changed the selector, which is front end now. And then we have the ports here. We have added a new section, NodePort, which is 31,000 in this example. Now this must be within this range. Is this needed? Is this must to have this range? You can modify this range, but would you want to do so? No. There is a reason why this range is fixed, because Kubernetes don't want you to have port collisions or use any well-known ports, which is why they have defined a specific range so that there are no port collisions. So I would ask you not to change the default range. Before I deploy the front end, before I run kubectl apply in the front end, you know that we are running a kind cluster, and for NodePort service to work, there are certain things that we must do. So let's first go to Chrome and go to kinds configuration, and you see that there is something called extra port mapping. So we'll have to do extra port mappings, and in extra port mappings we'll have to add these two lines. These are container port and host port. So before we write these things blindly in our configuration files, in our kind cluster configuration, let's see what these things will actually do. So I'll again go to my draw.io. I'll scroll this down and you see this is the configuration that we'll be doing. Everything remains the same. I have just added two new lines, that is container port is 31,000 and host port is 31,000. Now let's see what will these do. I want you to understand first that this is my Mac machine. My Mac has a Docker engine installed and I am running Kubernetes with kind. So I've installed kind, and then the supplied configuration, I've asked kind to create 3 nodes for me. These are the 3 nodes that are created for me. If I go to my Docker desktop, you will see that there are 3 containers running, and these 3 containers are running because this is what I defined in my configuration. You see, first node is this, second node is this, third node is this, and you see this exactly here. What I am saying to my kind is, whenever someone accesses my Mac machine on port 31,000, that is the host port which is for my Mac machine, you send that request to container port 31,000. Why container port? Because kind is my cluster, Kubernetes clusters control plane here is running on port, is running as a container, and that container must listen on port 31,000. So how the flow would look like? I hit this and then request goes here and then to my service. Now why I am mentioning this part here is because if you have deployed this into your original virtual machine, so if we would have deployed this cluster using kubeadm, and then if you would have run this command, then it would have shown you the IP of the nodes. In that scenario, you wouldn't have to do any of these configurations. You would just enter this IP address :31,000 and everything would have worked. But in our scenario, we are doing this because we have deployed our Kubernetes cluster with kind. As we move later in the course, we will establish a cluster using kubeadm, so you do not have to worry about that. But for this specific configuration, you will have to do this configuration in order for everything to stitch and work properly. Let's go to our console again. I'll clear my screen here. Then I'll run kind get clusters, only if I could spell, kind get clusters, I see there is only one cluster which is named my first cluster. I can also hit kind-h to see all the options that are available with this command. I want to delete this cluster. I'll write kind, then there is a delete flag, -h again, kind delete cluster, and the name of the cluster is my first cluster. I'll hit enter and it has started deleting. Now understand that my backend deployment is also gone with this command. So what I'll now do is I'll run kubectl create cluster. I'll write -h to see what all options do I have. Create, okay, create cluster. Why have I written kubectl? This should be kind. Please pardon me guys. Kind create cluster -h. If I write -h here, you see that I can supply the configuration and then I can also name my cluster. So what I'll do is, now I won't be supplying the image and all those things because those image part is already present in my, let me just close this, is already present in my configuration file. You see here, I have supplied the image here. Let's go here, kind create cluster -h. I'll have kind mentioned here. Sorry, not -h, config, and then I'll mention kind cluster here, and the name of my cluster would be let's say my second cluster. I'll hit enter. Now it has started creating the cluster for me. As soon as I hit that, if I go to my Docker desktop, you will see that the new containers are being created for my second cluster, and you see that this is also available here on port 31,000. But this will not show anything right now if I click here because I have not deployed any resources. So I'll just copy this URL, and now let's do one thing. Let's go to our console and just quickly deploy both front end and back end. So I'll go to my command line. I'll run kubectl apply -f backend. I'll create, and you see that there are two things created. First is the deployment, second is the service. Then I'll do the same for the front end. I'll hit enter. It says created. If I run kubectl get all, I'll see that the front end containers are being created, the backend pods are created. We have two services that we have just created, and then you have two deployments, and like we know, deployments will also create replica sets, which you can see here. Now let's run this command again to ensure that all our pods are running. So we are good there. Another thing I want you to see is, now you see 80 is the port of the cluster IP and 31,000 is the node port. In this example, 9090 is the cluster IP port. So let's now go to our Chrome browser. I'll add a tab. I'll write localhost 31,000. I'll hit enter and it says welcome to Nginx. Works like clockworks, right? We have practiced NodePort. We have practiced ClusterIP. We know that NodePort is used when you want to access your cluster externally. Now, we have seen that this is a nice way to access your services, but this is not the best way. I cannot go to my website users and tell them that you have these 10-15 IPs, and if some IP is not working, you go to a different IP. So that's something that doesn't work in production. Then why would you use NodePort? So NodePort can be used for testing, development, and we'll see the next service, that is the LoadBalancer service. That service also builds on top of NodePort. Just hold your horses for a little while before we disclose that thing to you. We know this is not a viable solution. We want something that will automatically choose a healthy node for you. Ta-da! Welcome the LoadBalancer service. Provide a single public IP with automatic failover, so no manual intervention is needed if a node goes down. Now let's go to our analogy again. What is happening here? Now we have a call center. Now user, instead of remembering these two phone numbers, just have to know the number of the call center, and then call center will then transfer the call to the healthy building, and then that is how a user can reach the HR department. Similarly, when I talk about Kubernetes, you have a load balancer outside. When user accesses the load balancer will direct the traffic, will forward the traffic to a healthy node, and then that healthy node will cater to the traffic. The traffic will go to again an internal service, because if you see this example, if the user wants to reach the HR department, the user first goes to the call center. Call center directs the call to the front desk, but front desk again uses the extension internally route the traffic to route the call to the HR department. Similarly, in Kubernetes, even when you have load balancer, you still need to have a NodePort. You still need to have a ClusterIP. Like here, even when you have introduced the call center, you still need the front desk phone. You still need an extension for the department that is to be reached. Now let's see the low level design of this. So what we learned is, first there is ClusterIP, then there is NodePort, and then there is load balancer. The load balancer is built on top of ClusterIP and NodePort. So when a user tries to reach the load balancer, user will type the public IP of the load balancer along with the port number, and then that request will be directed to a healthy node. Any of these nodes can cater the request. Let's say node 2 was chosen again. It will go to the 31,000 port of this node, and then this node will send that traffic, will forward that traffic to the ClusterIP, and then ClusterIP in turn will send that traffic to any of the available and healthy pods. Let's go here and see how it works. So what I have done is I created a front-end service, and the type of that service is now load balancer. Previously it was NodePort, now it is load balancer. We see that there is again a ClusterIP assigned, again a cluster port also exists. In this example, the ClusterIP port and the target port are both same. This is what you would see usually in production environments. And then you have a node port that is 31,000. And like before, there are 3 endpoints that are select. If I run a kubectl get svc front end, since I am working with kind clusters, I do not have an external load balancer. If you were on a cloud provider right now, if you were running, let's say, an EKS cluster on AWS, and if you would have run this command, it would have spun a load balancer on AWS, and that load balancer would have an IP address, and then you could have used that IP address to access your application. The traffic flow would be, you would access that IP address on, let's say, a port 80 or 443 that are HTTP and HTTPS ports. Then the request will be forwarded to any of the healthy nodes, then to the ClusterIP, and then ClusterIP will send the request to the actual pod. Since we are on kind, we cannot really practice that, but I want you to understand a high level view and a low level view of how a load balancer service works. Now there is a surprise for you. When you are talking about production grade applications, you would not see the load balancer service being used, because the modern applications are complex. They require things like host based routing, URL based routing, because certain requests I want to transfer it to, let's say, my iOS related deployment, and some requests I want to forward to Android users to the Android deployment. But how do I do that? So those things are not available with your plain load balancer service. We use something called ingress controller. So in production environments, you would not see load balancer service, although you would use this for testing here and there. But production grade applications will use something called ingress controllers. We'll look into what ingress controllers are in much greater detail when we move ahead with this course. But for now, I want you to understand that load balancer service is something that is not used that frequently. Let's move to the last service that I want to discuss today. That is the external name service. The name says forwards internal requests to external services by DNS name. Let's see what this is. Let's see this via an analogy. So we have the same office building complex, we have two buildings, but we have added a special functionality for our users. We have told our users that whenever they want to reach IT support, they just dial 111 and internally their phone system will transfer that call to the actual IT support, whose number is this, an external phone number. This is so helpful. My IT support, my department can use this one number to reach an external provider. That's pretty cool. Similarly, when I talk about Kubernetes, if I want to reach something external, for example, like we discussed that in production environments, you would always deploy your databases onto a cloud managed database, or you would be using databases on EC2. If you want to reach the database that resides outside of Kubernetes, then you can always use ExternalName service to do that. Like our building 2 was using, or building 1 was using 111 to reach an external IT support, similarly, our pods can use ExternalName service to reach external entities like a database server. Now let's see the low-level design. If you see this, whenever my backend wants to reach the database, they can use this name, CKA SVC. This is what we have created, CKA SVC. And the type is external name, and then we have an external name. This is the actual name of our database server, and this is our service which our backend pods will be configured to reach the appropriate external name. If you see this example, I have added 3306 because 3306 is the port on which MySQL runs. Let's assume that Amazon RDS is running MySQL in our scenario. So whenever the request will be for this service internally, Kubernetes will forward this request to the external name, that is Amazon RDS. Why would you do it to begin with? Why can't my application directly be configured to use this name, right? Why do I have to have another layer? For other services, we understand that we have those things because otherwise the communication would not have been possible. But here, why can't I configure this name directly in my pods? I want you to understand one deep thing. Whenever you are talking about production grade applications, you want to decouple as many components as you can, because this is a dependency. This is not the actual code. This is not the business logic. So you want external things to reside outside your application. For example, let's say if this Amazon RDS dies one day and you would have to create a new database. And new database that you create, the new DB instance that you will create will have a new name. Can't go into your container image and change the name in the application code itself. That's a cumbersome process. You first modify your code, then you have your Docker file, and then you create a container image out of that, then you push the container image, and then you upgrade your deployments to have the new container image. That's a cumbersome process. If let's say this name changes and I have an external name service, I'll just change the name here for the new database, and my application will still be communicating with this name, and this name will be redirecting the traffic to anything that is there in the external name. I just change the name here and all things are done. So for this reason, you have an external name service. I hope you have understood Kubernetes services. That's a wrap for this lesson. Today we covered why Kubernetes services are important, learned about different service types. In our next lecture, we will shift focus to imperative commands to quickly create deployments and services. If you have any questions, feel free to ask them in the comments section and I will reply. If this helped, do consider liking, sharing and subscribing. It will mean a lot to me. Thank you very much.